So what was the last topic we were discussing? We were not there last week.
Sir,
Yeah, tell me. Yeah, tell me, what was the topic we were discussing?
excess pressure in a soap bubble.
The excess pressure inside a soap bubble is what we were seeing. This one, right? This is the one we were seeing,
Yes,
right?
sir.
Okay. So the next topic that we are supposed to discuss is capillarity, right? So did we discuss about cohesive and adhesive forces? Can you tell me if we discussed this part?
No, sir.
So we didn't discuss this, no? Okay. So write down the next heading as cohesive and adhesive. So what does it speak about? So what do you mean by cohesive force? Basically, cohesive or adhesive force both are forces of attraction. Okay. So cohesive forces are basically the force of attraction that is existing between molecules of the same substance. Okay. So cohesive force exists for the molecules between the same substance. Okay. Next is, if you look at the example, what is the advantage of cohesive force if you observe, right? So cohesive force is mainly Like, for example, if you take solids, right? Why do solids have a definite shape associated with it? It is because of the strong forces of cohesion that is existing among their molecules, right? Now, the next question is, what is an adhesive force, right? So, what is an adhesive force? It is the force of attraction between the molecules of two different substances. In the sense, let's say you want to stick a paper to a you want to stick two papers, for instance. So two papers are two different objects. In between, what do you put? You put a glue. So the glue is called as the adhesive. And those two papers are stuck to each other due to the force called as adhesive force. So the force of attraction is existing between the molecules of two different substances. Then we call it as an adhesive force. The example is, it is due to this force of adhesion only what happens is ink will stick to the paper while writing. So when you're writing, no, your ink is getting stuck to the paper. Right, now you're writing. When you're writing, how is the ink actually getting stuck to the paper? Because of what kind of force? Because of adhesive force. Similarly, when you take a container and you dip it into water and take it out, what will happen? You will be able to see some water molecules on the side of the container. Am I right? And why is that happening? That is also because of the concept of adhesive force. Right? So here, the reason why we are studying this adhesive force and cohesive force is to understand an important concept called as capillary action. And in capillary action also, there is another concept which we need to understand, which is called as angle of contact. Okay. So if you observe, when you take water and pour it inside a container, again you empty the water, right? You can observe that the container will still be wet. Why is it happening? Because of, see, water molecules have cohesive force. Because water molecules are able to exist as water molecules only because of the cohesive force. Then what about the adhesive force that is existing between the water molecules and the container into which you're trying to take it, right? So what should happen? When will the substance, when will the liquid be able to wet the container? Only when the force of adhesion between the water and the glass molecules is greater than the force of cohesion that is existing within the water molecules. So are you able to understand what I'm saying? Are you able to visualize what I'm saying? Right. So if the adhesive force is greater than the cohesive force, then the liquid will be able to wet the container. Now you can ask me a question, sir. Every liquid is going to wet the container, but no. There is mercury. When you take it in the container, it doesn't wet the container. And why is it happening? Because the force of cohesion for mercury is more compared to the force of adhesion. Are you understand what I'm saying? Next. See, this concept of molecular range I already explained. So molecular range, based on this only, we discussed the concept of surface energy. We told that the molecules at the surface will have greater energy compared to the molecules that are present inside the packet. Okay, what is this molecular range? So range basically means some distance. Molecular, the name is suggesting it is some force that is existing. So the maximum distance up to which a molecule can exert some force of attraction on the neighboring molecules. Okay. So if I have one molecule here and another molecule here, there is a range between which the molecules will be able to interact among themselves. So that range is what is called as the molecular range. And it is of the order of 10 power minus 9 meter in solids and liquids. It is of the order of 10 power minus 9 meter in solids and liquids. Now, if you see, there is one molecule here, right? And for that molecule, if you draw a sphere around it, okay? If you draw a sphere around it, then You try to bring in another molecule anywhere within the sphere, that the second molecule will start experiencing food, because that sphere you have drawn, no, the radius of the sphere is what is called as the molecular range. So the radius of the sphere is molecular range. So that molecular range can exist anywhere in the space. And that sphere is what is called as sphere of influence. So when we are trying to study the behavior of molecule under the influence of cohesive force, we need to consider. So when you're talking about cohesive force, only the concept of sphere of influence comes into picture. So when you're trying to study about the cohesive force, what is that we need to take into consideration? We need to take the sphere of influence into consideration. And the next term that you need to know is something called as a surface film, right? So if you are able to think of a thin film of liquid near its surface, having thickness which is equal to the molecular weight for the liquid, then it is called as the surface film. Okay. These are all theoretical parts. The next concept is something called as angle of contact. The surface film is a top layer, surface is top layer. So there is a thin film that can be formed. Okay. So a thin film of liquid, which we cannot see because these are the molecular concepts which I cannot say to you with the naked eye. So there is a thin film of liquid which is formed near the surface. So that layer will have a thickness equal to that of that is. If that layer has a thickness equal to the molecular range for that liquid, then it is that particular surface is what is called. That particular layer is called as a surface. Next. The next concept is about the angle of contact. Okay. So generally what happens is when you take a container and you take liquid inside. Okay. So then the top surface of the liquid will not actually be completely flat. The top surface will not be completely flat, especially at the ends. Right? So the liquid surface generally will be curved when it is in contact with the solid. Why is that happening? Because of the concept of surface tension. So when you take a liquid inside a container, at the ends, if you see, there will be a small curvature that will appear, which will look either in this form. You're able to see one here. Right. You're able to see one surface here, the first one. The second one is bulged outwards, and the third one is completely flat. So if you look at the first one, if you take a glass vessel, and in the glass vessel, if you pour water, so for water, what is the special property that is there? The adhesive force is more than the cohesive force. So what you have to will be having the possibility to stick to the container. So those kind of liquids will form a layer which is curved in nature, which is called as meniscus. MENISCUS. It's called as meniscus. Okay. So when you see from the top, whatever shape you are able to see, then the prefix is given accordingly. So this is called as concave meniscus. So this one is called as concave meniscus, and this is called as convex meniscus. To understand this concept, so the shape that it is taking, right, the surface is taking, purely depends on which force is dominating. Okay. If the cohesive force is greater than the adhesive force, it takes a concave meniscus. If the cohesive force is less, if the, sorry, I repeat. If the adhesive force is greater than the cohesive force, it takes concave meniscus. If adhesive force is less than cohesive force, it takes a convex. If adhesive force is equal to the cohesive force, then the surface is going to be planar in nature. Now comes the question of what is this angle of contact? Listen to this carefully. So listen to this first. Listen to it. So angle of contact, okay, angle of contact is defined as the angle theta. So whenever you want to measure the angle, you measure it between two lines. I repeat it. Angle of contact is defined as the angle theta, which is taken between the tangent to the liquid surface, right? So between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid. So this point is important. Listen, guys. Listen, then you can write it. Listen to this. Understand the concept. So it is defined as the tangent drawn to whom? Drawn to the surface. Right? It is defined as the angle between the tangent drawn to the surface and which surface? And the solid surface. So when I say solid surface, see, if I have a concave shape like this, I can draw only one tangent like this. And this is going to be the solid surface. So when I take the solid surface, I can define two angles. What are they? One is alpha, and the second is theta. So which one should I call as the angle of contact? The angle of contact should be taken with respect to the solid surface, which is in contact with the liquid. So which one is in contact with the liquid? Theta. Similarly, when you take it like this, then this angle will be the angle of. Are you able to understand? So when you take the angle of contact with respect to concave meniscus, it will be acute. And when you take the angle of contact with respect to a convex meniscus, it is going to be obtuse. And when you take the angle of contact with respect to a planar surface, it will be 90. It will be 90. You don't call it as it's a liquid surface is plane. Only meniscus is used to it. The first one and second. The word is term, right? Next. The question is, the value of angle of contact depends on what factors? One is the nature of the liquid that is in contact with the solid, cleanliness of the solid surface, and third is medium above the free surface of the liquid, and the last one is temperature of the liquid. So what are the factors on which angle of contact depends on? First one is nature of the solid and the liquid in contact. Second, cleanliness of the solid in contact. Third, medium above the free surface of the liquid. And fourth one is temperature of the. So these are the four factors on which angle of contact is determined. Okay. Shall we proceed?
Yes.
Okay.
Sir,
Tell me.
well, for the third case, if addition is equal to cohesion, means will it wet or not wet the glass?
Which one? The silver vessel, no pure. It will wet.
Yes.
It will
Okay.
wet. Okay, but the wetness will not be made more to the extent of what happens with respect to the other case. So you
Okay.
have a silver vessel, silver glass at home. Just take some water, pour it off, and see how it looks. Okay. Next is when I see the previous stage we discussed about the angle of contact. Now the next concept that we are supposed to see is what happens to the liquid meniscus when you take the same liquid instead of a container, inside a narrow tube. Okay, let's see what will happen. So, shape of the liquid meniscus in a narrow tube. That is the next step. Please write it. So, if you consider a molecule O on the surface of the liquid in contact with the solid. Okay. So let's say there is a narrow tube. Inside the narrow tube, what is happening? You put the tube inside water. And what will happen? There will be a meniscus that is formed. So when that meniscus is formed, if you take a point O here, right? That point O is where it is on the surface. And also it is in contact with the solid. Very good. So when this is happening, then there are various forces of surface tension that can be defined as follows. Right. So one of the surface tension is going to be, there are three phases observed: liquid, solid, and outside you have air. Right, the gas is right. So if you see the various forces of surface tension at the boundary of the three phases order. So how do you define this? Remember, surface tension is always tangential to the surface. How is it going to be? It's going to be tangential to the surface. When that is the case, when you define the surface tension, right? When you define the surface tension between the liquid and the vapor state. If I take the curvature to be at point 2, if I take the surface tension E between the liquid and the vapor phase, between this direction, are you able to understand? Next. The surface tension between solid and vapor state. So this is the solid. So for the solid and the vapor state, the surface tension will take this upward. Okay. Whereas for a solid and liquid, we are going to take through in this direction. Okay. In such a way that this point is going to stay at equilibrium. Yes, sir. Right? This particle has to stay at equilibrium. Now you see this PLE, can I resolve it into two components? One is PLE sin theta, and the other one is going to be PLE cos theta. Can I resolve? This PLE is resolved into two components along the horizontal and along the vertical. So when I say this particle has to be at equilibrium, there should be another force existing which is able to balance the horizontal. So what the fourth force that is going to take is that is the force of addition. So having this return, then what is going to be the relation between force of addition and other parameters? So force of addition will be equal to TLV sin theta accepted. Am I right? So force of addition is equal to TLV sin theta. Similarly, TSV will be equal to TSL plus TLV cos theta. Then what will cos theta be equal to? TSV minus TSL divided by TLV. So what is theta called as? Theta is the angle of contact. Okay. So there is another way of defining what kind of meniscus you are going to get. Depends on this particular value. So cos theta is what? TSP minus TSL divided by T and B. Here. The next question is, okay, cos theta is equal to TSV minus TSL divided by T and B. Now, if cos theta is positive, then what is going to be the value of theta? The theta will be less than 90 and greater than 0. So what is it going to be? It's going to be an acute angle. So for acute angle, what should be the shape of the meniscus? Concave. So for it to be concave, cos theta is positive, means what will be the relation between them? TSV is greater than TS. Are you able to understand? Okay, when theta is positive, numerator has to be positive. So numerator has to be positive, means A minus B should be greater than A is greater. Then what about angle of contact being acute? Sorry, obtuse. At this time, TSV will be less than TSL. So if theta is exactly equal to 90 degrees, then we can see TSV is equal to TSL. Okay. Here. Okay. So after this, the last concept that we are supposed to discuss is capillarity. Shall we get started? Solution. So what do you mean by capillary? Why it is? Very simple problem. I hope others are also able to see it. To take a thin tube like this, right? Now, what will happen when you put inside this water? What will happen to the liquid inside straw when you dip it into water? This is water. Concave meniscus is already formed here. This is the solid, this is the liquid. The liquid surface is already having a concave meniscus here, which I told you, which will not be visible to the naked eye. You cannot see. Are you able to see some thin film there? Some thickness here. That is what is called a surface film. Anyways, now if I take this tube and put it into this liquid, what is happening to the water inside? What is happening to the water inside the straw? What is happening? Is it getting raised further? Are you able to understand what I'm asking? See, you are able to see the wetness. You are able to see a water drop. Now my question is, when I put this into the liquid, what is happening to the liquid inside? Is it not getting through this surface and coming up? Right? So it is coming through the surface and the liquid is getting raised inside the straw. Right? Now, how is this happening? That we will see. So if this kind of an action is able to be exhibited, then you call that as a capillary action. Okay. So what do you mean by capillary? It means, see, capillary is basically a thin tube, okay, which is called as a capillary tube. Where a capillary tube of a glass open at both the ends. So since I don't have a glass, what I did is I took a plastic straw, right? When you dip it, right? When you dip in a liquid which wets its walls. So what is the liquid that will be able to wet a glass wall? It is water. So when you dip it inside water, then what will happen is the liquid starts to raise inside the, and this kind of an action is called as, right, capillary action. right? Suppose you instead of having water, if you put mercury and dip this straw to wash it. Okay. Instead, you want to put mercury. Okay. Then what will happen is it will not release heat. The liquid will actually go down. And this kind of an action is what is called as capillary action. So the phenomenon of rise or fall of liquid in a capillary tube in comparison to its surroundings, right? The rise or fall of the liquid inside a capillary tube. So here what is happening with respect to the surface? The liquid is raising, whereas inside the mercury it is dipping, right? So this phenomenon is called as capillary. Now, based on this capillarity, what are all the real-time applications that we can see? So one is you see you take your pen, okay, take the pen nib and keep it on top of a paper for a longer duration. What we have to do, start spreading. So that spreading is happening because of the capillary action. Second is you have these lamps. For these lamps, what you do, you pour some oils and have a wick. So what is happening through it? Again, the liquid will get raised, right? So the oil is able to travel to the wick due to capillary action, right? Suppose there is water here. Okay. Suppose I spilled water here. If I take a towel and keep on top of it, what will happen? It will be able to absorb it. And how is it happening? Capillary action. So all these effects are because of capillary action. So if you use an ink pen, right? For the ink pen, you have a nib. So have you ever observed how the nib will be at the tip? There will be a line, right? So why is that split there? For the ink to flow from the pen through the nib to the nib. Through what action? In the same capillary action. So these are all the real-time applications of capillary action. Clear with this? Last topic is, we'll see how does the rise of a liquid in a capillary tube actually take place. Right? So the rise of a liquid takes place, and we are going to derive a formula for it, which is called as the Ascent formula. I'm not sure if this was mentioned. Did you get this problem? No? So there is something called as an Ascent formula, means the level to which the liquid has raised inside the capillary tube. Okay? With respect to the surface. So with respect to the surface, what is the height to which the liquid has actually moved upwards, right? So for this, what we are doing is we consider a capillary tube of radius r. So we consider a capillary tube of radius r, which is dipped in the liquid of surface tension sigma. Dipped in the liquid of surface tension sigma and density rho. Suppose the liquid wets the tube. So when the liquid wets the tube, what kind of a meniscus does it form? It forms a concave meniscus, right? So the shape of meniscus of water will be nearly spherical if the capillary tube is sufficiently narrow. So when you see, you will have a concave meniscus. But that concave meniscus, if you try to zoom in and see, when you zoom in and see, then you can see it will look like a part of a sphere itself. Okay, that is what they are saying. Then the shape of the meniscus will be nearly spherical if the capillary tube is going to be sufficiently narrow. Okay, one. The first diagram is rise of liquid in the capillary tube. Second diagram is going to be the enlargement. Right. So based on the excess pressure that is there inside the liquid form, I repeat it, based on the excess pressure that is there inside a liquid drop. Right? Can you tell me what the value of the excess pressure inside a liquid drop is given as 2 times P divided by R. It's given as 2 times P divided by R. So this we saw in the previous class. Okay. So when I say this is an excess pressure, this is not an absolute pressure. This is excess with respect to the outside. Right. So as the pressure is greater, now you tell me logically which side the pressure is supposed to be greater. For something to get bent in the downward direction, which side the pressure should be more? The outside pressure is more compared to the inner pressure. Why is it so? Only then you can have that kind of a shape being formed. Right? And there will be a pressure just below the surface. What is the value going to be? This 2P divided by capital R, where capital R is going to be what? Capital R is going to be the radius of this meniscus. Okay. So the excess pressure is equal to 2P divided by capital R. But if you look at this diagram, capital R is like this. Small r is going to be the radius of the tube. So capital R is what? Radius of the meniscus, and small r is going to be the radius of the tube. And this theta is going to be the angle of contact. So theta is going to be the angle of contact. So when you keep shifting it, right, when you keep shifting the angle, then at this point it becomes theta. Okay. Now, what will be the relation between, listen to this carefully, what will be the relation between capital R and small r? So, can I write small r divided by capital R is equal to cos theta? So, small r, capital R will be equal to R divided by cos theta. I'll take this value and put it here. Then P will be equal to 2P cos theta divided by small r. P cos theta divided by small r. Okay. Here. Okay. Now see, why is the liquid getting raised? Why is the liquid getting raised? Obviously, there should be some pressure, right? So, due to this excess pressure, the liquid rises in the capillary tube to height h. Now, that height h column is there, the height to which liquid has got raised. Correct. So, what is the pressure exerted by the liquid column at a depth h? What is the pressure exerted by the liquid column at a depth h? It is going to be rho g h. Okay. Now, what we can do is, if you equate this 2T cos theta divided by small r to rho g h, you get h is equal to 2T cos theta divided by rho into g into r, and this is going to be the height of ascent, or you can call it as the ascent formula. call it as the ascent formula. For this chapter. Okay. Now we'll do some activities that are for both to discuss. Together, and they are not able to see. What I can explain to you. Very responsive. You know what is the next chapter we are supposed to discuss? தெரியுமா தெரியாது?
Thermal expansion, sir.
What is that? Come here. Then what? Oh, basically. Then what? Okay. Guys, are you able to see?
Yes, sir.
See. Okay, we'll get started. Started. Okay, come here. What do you have here? What is this? Water. Is any idea? No. Standard. Yeah.
Spice.
Do you ever walk into kitchen? What is it? Pepper. Okay. See, when the pepper, you have this water, and on top of this, I sprinkle this pepper. Right. So what is happening? So what is that you're able to see? For those who are online, I'll show it to you. So what are you able to see? Nothing. So that it is just the pepper is going and sitting on the surface, right? But my question is, how is that surface, how is the pepper able to go and sit on the surface? So what property of the liquid is actually helping the pepper to get settled on the top? Answer. Because of the surface tension. Because this is the surface, on top of it, it is able to hold some particles, right? Now what we want you to do is move these particles by touching it. See what you put your finger and look. One other acid flow. Just the surface touch. This is the reaction to the paper. What you do is, you know what is this? So just dip your finger in it and touch the surface. So what is happening to the water form? Actually, this is diluted a lot. Either thicker. Actually, now it will not work. I'll show you. 1 minute. Repeat start. Okay. இப்போ எடுப்போம் என்ன தேவையில்லை தேவை அது நான் பார்த்து அதை வச்சு ஓகே ஸோ உன் கையில் வேறு எதுவும் இருக்கா ஹேண்ட் வாஷ் ஏதாவது பண்ணிட்டு வந்தீங்க your hand is fresh you touch soap right? Now see when this pepper is there no I touch and take it out what is happening the pepper is actually sticking to my hand so I'm not able to see any reaction but what I'm going to do now is instead of me dipping my empty hand I've taken a little bit of soap solution and if I keep on top of it what do you think what is your expectation pepper will move or the pepper will start falling down? It will start falling down. But what happened? Did you see what happened? Did it fall down? Guys, did you observe what happened? So the pepper started moving away. This was it will start moving away. I've done something with respect to this water. Can you tell me what is the science involved in this? Any guess of what would be the science involved behind this? So what exactly has happened? So surface tension is the right answer, but what exactly did we do? Did we increase it or decrease it? Yes. We decreased it. That's right. So what exactly happened is initially the water molecules were held, right, due to the cohesive force. On top of which we put some pepper, right? And the water molecules were holding that pepper as well. But when you dip the hand inside a soap solution and kept it there, what happened? You actually broke the surface tension, right? Due to which the water molecules started moving away. When they moved away, they carried the pepper particles also along with them. And this is what has happened with respect to surface tension. Are you able to visualize this? Right, there's a very simple activity. Similarly, in your textbook, they would have given you a definition like you keep a pin on top of it, it is going to float. So when you see from this side, you can actually see a small curvature. That experiment you have to do it with. If you don't pull the paper properly, so that part I'm not doing it. Okay. Now, the next part is material like scratches candle. Can you help me move that? Wood piece ஏதாவது சின்ன பீஸ் கூட இல்லையா சின்ன பீஸ் Okay. Now I have a question. So I hope those who are online are able to see, right? Yes or no? Those who are online are able to see?
Yes, sir.
Yes, sir.
So listen. Hold this. So what do we have here? Cut. Camera cut. What do we have here? So what do we have here? Cut. You tell me what is this? Balloon. This is a balloon that is filled with air. What do you have? Balloon with some liquid. Okay, that is water reaction. Okay. Now I have a question. If you bring this balloon near the candle, okay, no idea. At least have a guess, no? What will happen? It will burst, it will take some time, it will get heated up, it will expand. Some answer will be there. Burst up. Okay, hold it at the top and see. Hold it at the top, bring it close and see. Nothing will happen. Burst up. Now, what do you think will happen here? So what will happen here? Nothing will happen. Sure. Can you please it there? Can you hold it for something? Right. So what has happened? So you are able to see some. To keep it for some more time. One thing that you are able to see is the amount of time that it took, right, to burst. This one did not take time at all, right? It is not bursting, though you keep it for a longer duration. Why is it happen? Water. Because the water is. So have you heard a term called as specific heat capacity? You've heard of it. So what is specific heat capacity? The amount of heat that we need to supply to raise the temperature of unit mass of the substance by 1 degree Celsius or 1 Kelvin, right? So for air, it is going to be this compared to that of water. Means you need to supply more amount of heat to raise the temperature of water. That is the reason why for air, the immediate burst took place, whereas with respect to water, it took some more time. Are you able to understand? Right? So this is all about the specific heat capacity. Guys, are you able to understand? Those who are online?
Yes, sir.
Right. Okay. Now, did you see when the balloon burst, the candle was switched? Right. Now, I have another question. You want to put this off? Put it off. Blow it or do whatever. Don't keep your hand. Okay, don't burn it. Just blow it off. Whatever. Did I touch it? Right? Guys, did you observe what happened? Should I repeat it? Those are online. Right? Nice, no? It's fun. How is this happening? What science is involved? At least guess, no? So, what is actually helping the candle burn? This wax, right? Yes, oxygen is definitely there. The wax is there, no? So, when you switch it off, the wax is getting evaporated. So, when you take that fire closer to the wax, right? Again, it travels through the smoke that has come out and it is again going in. Okay, there's an example of a combustion reaction. Right? Are you able to understand what I'm saying? Okay. One challenge. Ready to do? Okay. I don't want you to try one with run. You'll burn your hand. இவங்க இருக்கானுங்களா தூங்குறானுங்களா தெரியும். Dude, I slept off. Very good face. Burn முடிச்சு இவனுக்கு ரெஸ்பாண்ட் பண்ணல. ஸோ ஓகே, டைம் என்ன? 6:54. Okay, I just want to ask you one thing. I'll show you. I'll show you. See, take a it. Okay. So I've taken this, you're able to see the fire. I'm able to hold the stick. Will I be able to do the same thing like this? So if I hold it like this for some time, what do you think will happen? Okay. So let's see how many seconds there is. But if it is hot, drop it. Now, this drop. Okay. I'm looking at edge of it. Mastic worker. You right? So I want you to hold it vertically. Like I know what will happen. Drop it. What happened? You burned it. Did you burn your hand? No, right? So why are you not able to hold it like that?
The flame is bending towards you.
The whole bending it. See, when you hold it like this, nothing is happening. But when I hold it like this, I'm not able to hold it. I'm able to sense some heat. Why is it so? Because this is actually heating the surrounding air particles, and those air particles are actually hitting my hand. But the question is, will I be able to hold it in that way for a longer duration? Then what I need to do is, I need to keep see what I'm going to do is, I'm going to keep it revolving like this. You're able to see? By doing so, what exactly am I doing? I'm actually not giving enough time for the surrounding to get heated. Whereas when you keep it exactly straight, you are actually heating up the air particles around it. That is why your hand you'll be able to sense that burn. So this is also again another phenomenon where you can say that oxygen is supporting combustion. That is one thing. And at the same time, you can say that the air particles, in terms of physics, if you speak, the air particles surrounding this fire are getting expanded, right? And they are getting heat, which is spreading to your hand. So though you directly don't touch the fire, you still sense that heat. You're able to understand? So what are you supposed to do? Just revolve it so that you don't give enough time for the air particles to get heated. Frida, are you able to understand? Don't do these experiments at home. Okay. See, this one you can try and see. Go home, try and see. Or you can show it to your people also. Just keep it away and start burning as it can show you. But you know what is the science behind it, right? Nothing sound done. Okay. So thermodynamics also I'll do some activities and show you. Okay. So for today, that's it. I want bigger class. Okay. Need Oh.